Hello, folks. Good to see you all. So it's time for us to start talking about Faraday's law and all of the math that's involved. And to do that, we're going to start with a quick little review. So when we began our sojourn into the world of electricity and magnetism, first thing we ran into was Gauss's law. And basically what Gauss's law said is that if you figure out or if you determine the electric flux through a closed surface, it was going to be proportional to the amount of charge that was enclosed inside the surface. So you were introduced early on to this idea of a flux, a vector field passing through a surface producing what we called a flux. And you were introduced to the mathematical definition. You take the vector field and you dot it into either the area or a differential area. And then if it's the full area, you're done. And if it's a differential area, you have to integrate over all the little pieces to get the total flux through the surface. Okay, so you're good with this, hopefully. We then got into magnetism, and you ran into Ampere's law. And Ampere's law effectively said that if you have a bounded path in space, the circulation of the magnetic field in the region around that path was going to end up being proportional to the amount of current that passed through the face of that path. So here is your bounded path. If you had current passing through the face of the path, you would end up having some non-zero circulation of B around that path. Okay, this is a very obscure way of saying that if you have a current carrying wire, you will generate a magnetic field. So the question arises, if current carrying wires generate magnetic fields, is it possible to take a magnetic field and somehow or other with it produce a current? And so that's kind of where we're going with this next section. To do this, we need to kind of review what's going on with magnetic flux. So in this particular case, you're not going to be trying to figure out what the magnetic flux is through a closed surface the way you were with Gauss's law. You're going to be trying to figure out what the magnetic flux is through an open surface, the open surface being the face of a coil. So in this particular case, you've got magnetic field lines, you have a coil, you have its face, which is to say the area that's bounded by the coil. You have an area vector. Okay, area vectors are always perpendicular out from the surface. You have an angle between the line of B and the line of A, and the magnetic flux through that surface is going to end up simply being B dotted into A. Okay, and this assumes that B is the same everywhere, or its magnitude is the same everywhere on the surface. You will run into problems where the magnitude changes from point to point. Then this becomes the integral of B dotted into dA. But that's something that we'll worry about that later. For now, let's just be happy with this nice general expression, the easy expression. And I guess the last thing to point out, at least for this slide anyway, is that the units for this thing are Tesla meters squared. So B is Tesla, A is meters squared. This quantity is given a special name. It's called a Weber, which I've often been partial to. I think that's kind of a fun name. All right. So this is Mr. White's set of slides that basically says the same thing. So you'll find this in the pack if you go through the PowerPoints. Okay, so an observation that we need to make before we can actually get into Faraday's law. Let's say that you have this loop that is in this magnetic field. So the magnetic field, this region's got a magnetic field. The magnetic field is going into the page. This is just a standard coil, happens to be rectangular. It's moving with some velocity across the page. An interesting thing happens when this kind of a situation occurs, if you were actually to try it. What you would find is that positive charge would accumulate across this across the top here, and negative charge across the bottom. I don't know if you can hear the rain on my roof. It's kind of fun. And in fact, you can actually explain why that would be the case using classical theory of magnetism. You have free charge in the wire, assuming it's positive charge that can move around. So you've got, positive charges that are moving in this direction. You have a magnetic field that's into the page. There'll be a force up on that positive charge, which means that the positive charge is going to migrate this way, and it's going to migrate this way. And the net effect is that you're going to get this accumulation of positive charge up here and negative charge down here. So you're going to get this polarization. And in fact, that will continue until the electrostatic repulsion, because of all of this positive charge, and this QV cross B, this magnetic force that's forcing charge up here, this will continue until they equilibrate. All right, so the question arises, what ends up happening? Before the question arises, minor point, this is an example problem Mr. White came up with, which is kind of fun. You have an airplane that's flying from LA to Seattle, so it's moving northward, and it's moving through the Earth's magnetic field, and it's undergoing a motional EMF. So that situation with the coil going across the page, that's referred to as a motional EMF. The electric field that is motivating those charges to move is referred to as an electromotive force. Okay, so minor point, but whatever. So this is a situation where if you have an airplane that's moving in a magnetic field, that's like a coil that's moving in a magnetic field. You're going to end up having charge flow, and you're going to have charge accumulating. So one wingtip is going to end up being positive, and the other wingtip is going to be negative. And so this problem is basically asking you to figure this out. And I'm not going to take the time to do it. If you want to go into the slides and do it, you can. But it's kind of a fun little problem. So anyway, moving along. The question arises, what's going to end up happening once the coil tries to exit? And what's going to happen is that you're still going to have this EMF, this electromotive force, that's going to be trying to push positive charge in this direction, again, assuming it's positive charge that can move. But because there's no magnetic field out here, that force won't exist. And the consequence is that you're going to end up getting a current flowing in the coil. And as I said, you have just explained this phenomena using the classical theory of magnetism. Now the deal is that Faraday didn't view it this way. Faraday looked at this problem from a different perspective, which is what we need to kind of get into. So there's our magnetic field. There's our coil. What Faraday observed was that this coil, in this situation, there's a magnetic flux through that coil. There are magnetic field lines that are passing through that coil. And so there's a magnetic flux. And you can calculate it, B dotted into A. You could do the calculation. But what Faraday observed was that the magnetic flux was not changing. There was no change in the magnetic flux as the coil was moving across. And the observation was that when there was no change in magnetic flux, you got no current. On the other hand, when you got into this situation, now the magnetic flux is diminishing. You have fewer magnetic field lines through the face of the coil. And when the magnetic flux was changing, then you noticed an induced current. So apparently, changing magnetic flux generates current. And not only is it changing, but it's the rate at which it changes. If it changes fast, you're going to get a big current. If it changes slow, you're going to get a small current. So he could have related this change in magnetic flux with time. He could have related this to the induced current, but instead, what he did was to relate it to the induced EMF that was setting up the electric field that was motivating charge to flow. And so this slide is just reminding you of where you have run into this idea of an EMF before. If you think about, real world batteries, they have internal resistance. They also have this part of the battery that generates an electric field that motivates charge to flow. We quantified that with what we called an electromotive force, an EMF. Okay? So this is the same kind of thing. As far as Faraday was concerned, there was an EMF that was being generated. It was related to the rate at which the magnetic flux changed with time. It was proportional to it. To make it into an equality, you needed a proportionality constant, which happened to be the number of winds there were in the coil. You needed the negative sign for conservation of energy, which is something we'll talk about later. But in any case, this right here is Faraday's law. And if you put in, the definition for flux, B dotted into A, and then expanded it, then basically Faraday's law, kind of the working version, looks like this. So the technique for doing Faraday's law problems is really pretty easy. You basically figure out what the flux is through the coil that you're looking at, and then you take its derivative. That's how you do these problems. So this is a very simple problem. You have a 200 wrap coil. You have a perimeter. It's a square. You know what the sides are. You know what the resistance is. The field changes from 0 to 0.5 Webers per second in 0.8 seconds. So this is an example of a situation where instead of taking the derivative, you're actually going to end up using deltas. So B times A times the cosine of theta, that's this. B is changing. So you have change of B over change in time. Okay. A was not changing, so you could have pulled it out. And there it is. The cosine of the angle wasn't changing. You could have pulled that out. And there it is. Basically, you put in the numbers and you come up with the solution. The main reason why I'm showing you this, though, is the second problem. And the second problem says, what's the magnitude of the current? And what's important here is that in problems like this, Ohm's law still works. It's just that the quote-unquote voltage in the system is the induced EMF. So basically what Ohm's law says is that the induced EMF is equal to the induced current, which is what you're trying to figure out, times the resistance in the circuit. And this is actually important because you're going to need this later. There's another problem that's kind of a classic that is kind of cool. So you've got a ramp and a ramp, and you have wires with a resistor, and then you've got this rail. And you know the distance between the ramps is L, and you define the distance between here and where the rail is as X. And the question is, what's the induced EMF if you force this rail to move with velocity V to the right? Now, if you think about what's going on conceptually, the magnetic flux is increasing. Okay, you're getting more and more and more field lines in the coil because the coil is physically getting bigger. So you have a changing magnetic flux, which means you're going to get an induced current, even though there's no power supply in this thing, which is kind of wild. How do you figure it out? Well, the first thing you have to do is to figure out what an expression for the magnetic flux, because that's the thing you're going to take the derivative of. So there is the expression for the magnetic flux. It's just B dotted into A. Taking the derivative, B is a constant. The length L is a constant. So you're effectively just taking the derivative of x, dx to t is the velocity. Voila, there you have the induced EMF. So this is actually a lot easier than what the honors folks have to do, because they have to do everything with deltas because they're not allowed to use calculus, because they're not supposed to be using calculus in the honors class. So you guys actually have the easier problem, just because taking a derivative is so easy to do. In what direction is the induced current in the circuit? Well, you've got a current in a magnetic field. You know that F equals IL cross B. So you could use that to figure out what the direction of the force is on the charges moving across here. To do that, you'd have to figure out what the direction of the charge flow would be. This is not an altogether, I mean, you could do this, and it would be kind of a pain to do. It turns out that there's another approach for figuring out whether current is flowing counterclockwise or clockwise in a circuit like this. It's related to what's called Lenz's law, which you will be learning shortly. So it turns out in this particular case, it would have been counterclockwise, but I don't really want to go into the ins and outs of this just because it would take time, and it's much more easily done using Lenz's law. And so I'm just not going to take the time to do it. You will learn Lenz's law shortly. The current in B, you got this current, okay, this induced current that's flowing through this whole thing, but it's also flowing through the rail here. That current is itself in a magnetic field. Well, currents flowing in magnetic fields feel forces. How big is the force? Well, you know that F is equal to IL cross B. You know L is this length. You know B, that's given. All you need to do is figure out I. How do you figure out I if you know what the induced EMF is in the circuit and you know what the resistance? Ohm's law. Okay. So you go ahead and you take your IL cross B, you use Ohm's law for I, and you come out with B squared L squared V. And then the last problem, the force must be provided, a force must be provided to make the bar move with a constant velocity v. How much power must that force provide to the system? So power is the equal to the amount of work per unit time that's required. Work is F dotted into delta X over time. Delta X over delta T is just V. The force you've already figured out. And so you finally end up with B squared, L squared, V squared over R, which interestingly enough equals the EMF squared over R. Okay. Power relationship, V squared over R is one of the power relationships that you have. And then the last problem, which is kind of a stinker, is the outside force motivating the bar to move with a constant velocity v is removed. If its velocity starts off at v naught just before the removal, what's the bar's velocity as a function of time? Assume the rails are frictionless and the bar's mass is m. So I want you to pause this for a second and think about how you would go about figuring this out. So go ahead and pause and just think. And then when you're done, come back. Okay, so hopefully you're back. I'm hoping that you're realizing that this is going to be one of those wonderful Newton's second law problems where you take the force and put it equal to ma, except A isn't really A, it's actually dV dt. And then from there, you go ahead and manipulate. So it turns out that the force is a function of V. And so you've got to manipulate. So here is the force. Here is ma. You're going to bring the v down. You're going to bring the dt up, which is the same as multiplying dt on both sides. But whatever, you get the idea, you know how this works. You end up with dv over v, which you're going to end up having to integrate. You're going to have this thing times dt, which you're going to integrate. You're going to end up with a log function. You're going to have to raise it to the e. By the time you get done, you're going to end up with this velocity function. And it looks like my little picture here is in the way, but when you look in the PowerPoint, you will see that this actually can be written as V is equal to V naught e to the, I think it's gamma t, or it might be minus gamma t. It might be minus 1 over gamma t. I'm not sure which. Actually, it looks like 1 over gamma t. But in any case, the point is that you can go quite a ways with these Faraday's law problems, even to the point of using Newton's second law and some of the math that you learn during the first semester. Anyway, so that's it for this video. Kind of a long video. I'm sorry it took so much time, but most of this stuff is in the PowerPoints if you want to go and look at it there, or you can look at the video again if you want. Anyway, that's it. Be cool.